Hello everyone, my name is Evan Bean, and today I'll be talking about the severe inflammatory response syndrome propagated by COVID-19, its treatment methods, and other novel research going into it in the field right now.
Throughout the latter portion of the semester, we spent a significant amount of time learning about the mechanics of the cardiovascular and pulmonary systems and their associated action potentials. Today, I'm going to be discussing some of the chemical drivers of these systems and their interplay with the SARS-CoV-2 antigen and its associated serious inflammatory response syndrome, SIRS, as well as some of the novel treatment options that are being developed to combat serious organ damage with COVID-19 and future respiratory illnesses. Before diving in, it would be good to remind ourselves of the primary motors of arterial pressure regulation. There are three primary gateways to modifying arterial pressure: cardiac contractibility, controlled by the strength of the heart's compression; vascular smooth muscle contractibility, controlled by the compliance of any given blood vessel; and the regulation of the blood volume in any given system, controlled primarily by neurological signaling and hormonal activation. The latter two mechanisms mentioned are controlled by arterial baroreceptors, signaling bodies that produce an action potential upon the change in force of stretching or contracting a vessel surface area, a direct function of blood pressure. Similar to the cochlea, these baroreceptors record various and selective pressure ranges and also have the ability to signal in varying speeds depending on the rapid change in pressure of a system. One of the systems initiated by these baroreceptors is the renin-angiotensin-aldosterone system, or RAAS for short. RAAS is initiated by the release of renin from the afferent arterioles of the kidney's glomeruli from ports known as juxtaglomerular cells. Now, while this is a primary activation complex of the RAAS system, it's not the only one. The primary nervous system commands the renal sympathetic nerves, often commanded by fight-or-flight reflexes or strenuous exercise, and decreased sodium concentration in distal tubules, which you may remember is caused by localized decrease in blood pressure and can be sensed internally in the JG cells and therefore release the renin immediately. But naturally the question rises, what is renin? Renin is a hormone that cleaves soluble angiotensinogen, a liver-produced peptide found nearly homogeneously throughout plasma, forming angiotensin 1, reducing the peptide to a 10 amino acid long fragment. Angiotensin-converting enzyme, also known as ACE1, then cleaves an additional 2 residues to form angiotensin 2, a factor that promotes vascular constriction and the release of the hormone aldosterone from the adrenal cortex. It's also worth noting that with high concentrations of Ang2, there is a strong correlation with release of different cytokines, as Ang2 left unrestricted is a pro-inflammatory known for organ damage. However, if you regulate the system, it's actually quite useful. Ang2 is used to inflame blood vessels, which can then increase the resistance against blood flow, therefore increasing blood pressure. So if the RAAS system was activated when you had low blood pressure, it would be very good. And that's exactly what it's meant to do. And while that pathway is being followed, aldosterone, the hormone I mentioned before, activates potassium ion channels, releasing potassium into the tubular lumen while promoting water and sodium reabsorption in salivary and sweat glands as well as the stomach, which combinatorially, it increases the fluid concentration in the body, which then promotes higher blood pressure and fluid retention. The challenge then becomes regulating this process. If you have too much angiotensin 2, or if you have too much aldosterone, and it's left in your bloodstream, it can lead to serious damages. You can have too much potassium in your bloodstream, too much sodium in your cells, too much water in your cells. It's an unsustainable activation that needs to be regulated. And thankfully, once angiotensin 2 is secreted, it enters a competitive crossroads between performing its aforementioned functions and being metabolized by the enzyme ACE2 to produce angiotensin 1 through 7, a molecule that forms a complex with the protein-coupled receptor MAS. Now, interestingly, the MAS Ang1 through 7 complex is a counterbalance to most of the Ang2 processes. It can be observed as being anti-inflammatory and as a fluid releaser and as a tension dissipator in cardiovascular activity. So between the two, blood pressure tends to equilibrate at a reasonable pressure, and if outside forces govern it in a different way, more renin is released or more Ang2 is metabolized and it is reequilibrated. Now, unfortunately, one of the aforementioned enzymes may sound a bit too familiar to some of our listeners. ACE2, aside from its regulatory role in the RAAS pathway, is also the viral enteral protein for the SARS-type virus family. And during the COVID-19 virus, there's been a lot of research going into the effects that ACE2 inhibition by SARS-2 infection has. As you can see here, the formation of the binding complex between SARS-type virus spike protein and the ACE2 receptor does not directly inhibit the function of the receptor, which is shocking due to the observed reduction in flexibility of the enzyme. However, in titers, it's been demonstrated that exposure to SARS-CoV-2 will downregulate the concentration of ACE2 along the epithelial of lungs and kidneys and livers and the heart, wherever ACE2 most commonly appears. These organs are also the most common targets for serious organ damage from the SARS-CoV-2 virus. Now, obviously, one can say that regions that have the most ACE2 in them would be the most likely to have a virus attack them because they're the most active sites where a virus can bind onto a cell and enter and propagate. But there is reason to believe that the downregulation of ACE2 is the direct cause of some of the organ damage witnessed in COVID-19. In a mouse model performed with ACE2 knockout mice, it was determined that mice without the ACE2 gene had significantly higher titers in collagen and hydroxyproline, signifiers of vascular damage and oxidative stress. It was also found in that study that after exposure to the lung toxin BLM, higher rates of lung and vascular damage were observed than in the ACE2 in counterpart controls. So when we're looking for causal treatments for ACE2 downregulation and Ang2 overexpression, we only have a few options. First, we can look towards inhibiting ACE1, which would dampen the production of Ang2, and then your body would have to rely on secondary methods of regulating its cardiovascular pressure. You can also use blockers of angiotensin II receptors to water absorption and vascular resistance. And then your last option would be introducing large amounts of soluble ACE2 that is not connected to any cell lining into the areas of interest, such as the lungs and hearts, such that the spike protein from SARS-CoV-2 would bind onto it, be neutralized, and be removed from the body. The added bonus of this is that during infection, these ACE2 receptors in a soluble form could perform the roles that the epithelial ACE2 would normally perform by regulating the RAAS process. And each of these methods have their own pluses and minuses. Namely, angiotensin receptor blockers and ACE inhibitors are already widely used for the treatment of hypertension, heart failure, etc. They're on the shelf, they are readily available by hospitals, and they, in the past, have shown no significant side effects. However, with a virus that goes after ACE2 receptors, it is important to note that these two treatment methods do upregulate epithelial ACE2 expression, which gives viral entry a more probabilistic opportunity to get into host cells. And because of this, in studies performed with both inhibitors and receptor blockers, it was noted that no significant patient outcome was changed, unfortunately. In fact, a study of over 12,000 patients showed that there was no association between the use of ARB or ACE1 inhibitors and the severity and mortality of COVID-19. All that being said, the soluble recombinant ACE2 that has now been proposed has shown to aid patients with severe coagulopathy by upwards of 30% efficacy, and also been shown to inhibit SARS-CoV-2 attachment to the host ACE2 by binding to the S protein, inhibiting it, suppressing viral growth efficiently in vitro, and improving severe lung inflammation in vivo. It's gone so far as to pass through phase 2 and phase 3 trials with no deleterious effects. However, there still are some severe risks with this method that have not been purely examined yet. Namely, soluble ACE2 occurs naturally in the body and is often correlated with increased cytokine expression, as mentioned before. So with patients that are immunocompromised, for example, that cannot support an anti-cytokine storm response, this may not be a proper option. As such, there are new medical advances to handle such patients, using more or less a familiar technology, dialysis. In August of 2020, the FDA approved a host of CRRT, continuous renal replacement therapy devices, by the company Baxter. In this style of therapy, host blood is passed across a semipermeable membrane with a concentration gradient from one end to the other, in which the blood has a higher concentration of impurities than the dialysate. This allows these impurities to cross across the membrane and reach some form of equilibrium. Both channels are operating at a continuous fluid flow in opposite directions to promote as much diffusion as possible. The blood flow is also under higher pressure than the dialysate is, which forces water to cross across the membrane osmotically and hydrostatically. A unique phenomenon called solute drag brings some of the impurities of the bloodstream across while the water passes through. However, removing so much water requires that water is eventually returned back to the bloodstream. To facilitate this, there's a pre-blood pump that dilutes the blood prior to injection into the effluent pump that prevents blood clotting during the filtration. And after filtration, there is a post-filter replacement pump that adds water and saline back into the blood so that it matches the concentration required in the bloodstream. And while this is often performed on patients suffering from liver or kidney failure associated with SARS-CoV-2, there is research now going into using this method to remove angiotensin II and other toxins in the bloodstream that are propagated by the downregulation of ACE2 as a means of preventing COVID-induced hypertension, inflammation, and organ failure. With any of these measures being taken, acute respiratory disease syndrome may be stopped prior to its inception, where the cytokine storm is not initiated due to significantly lower expression of the chemicals that propagate it. If ARDS sets in, though, there is hope and research going into a adjustment to be made to CRRT that can help white blood cells combat the cytokine storm by applying a selective cytopheric film to the extracorporeal membrane cartridge used in CRRT. In low ionized calcium environments, the most active neutrophils and monocytes in the blood pouring through the CRRT is bound to the SCD membrane. As such, over time, the only white blood cells left in circulation are those that can promote an immune response, but not one deadly to the host. All of the aforementioned therapies are not fully developed yet and are continuing investigation. However, these types of therapies are extraordinarily promising in the development of new generalized applications for a potential of wide mutation in SARS-CoV-2. Presumably, ACE2-based therapeutics will work against any virus that is an ACE2 spike protein-based virus, and methods that help reduce cytokine exposure with some form of selectivity are heavily needed. Thank you very much for your time, and if you have any questions, I'd be happy